Like Nir was saying, in the first day of this gathering, you saw some introductions into NLP. And today I'll show a bit more details about how we use NLP for biomedical search engines, for biomedical hypothesis generation, and also for clinical outcome predictions in the literature. So we'll see NLP also on EHR notes by physicians and also on information from the literature and from biomedical knowledge bases. But before that, let me start with a bit of history. So what you see here is actually the first ever scientific journal published back in the year 1665, a long time ago. And this journal published on just about anything you can imagine, from planets in outer space to whales in the ocean. So if you were a scientist back then looking for knowledge, this would probably be one of the only places to go. If you fast forward to today, of course, there's not one, but many, many scientific journals. And to find knowledge and information, you'll use something like a scientific search engine, like Google Scholar, for example. And you're much more likely to come up with something like this, a whirlwind of research papers, many millions of papers, many millions of authors across many, many topics. An example particularly acute and also particularly relevant to this audience is the explosion of biomedical information. Over 1 million biomedical papers are added only to the PubMed index, with a huge wealth of potential knowledge. And it's not limited to only the literature. You have also scientific knowledge bases, resources, code libraries, online discussions, of course. And all of this huge wealth presents us with a really dramatic opportunity. With AI systems that can harness humanity's collective scientific knowledge in the literature to help us do better science and also potentially make better clinical decisions. Now in theory, it's all at the tip of our fingers, right? We have PubMed, we have Google Scholar, we can just find anything we want to help us with whatever task we have at hand. By the way, am I speaking in both microphones? Maybe I should just... Yeah, okay. But of course in practice it doesn't really work like that. We as mere mortals are very limited in our ability to sift through such a huge amount of information and synthesize it, combine it into decisions and conclusions. And our current technology for interacting with all this huge amount of information is very limited. In particular, these standard keyword search engines, returning long lists of results, making it very hard to discover knowledge and connect the dots. And also they assume you know what to search for in the first place and exactly what keywords you need. So in my research overall, I focus on what I call task-guided knowledge discovery. So how do we assist researchers and clinicians throughout their diverse tasks? And speaking about clinicians specifically, I'm sure a lot of you have heard of this fundamental paradigm of modern medicine, which is evidence-based medicine, or EBM, which calls for finding the best, latest evidence from the literature to help support clinical decision-making. Now, there's this nice systematic review from JAMA from a few years ago that first looked into all the different types of questions that clinicians have. And these are questions where they don't feel that they have the answer immediately. They need to think, or they need to potentially find knowledge externally. And then beyond kind of codifying these different questions, the systematic review had some interesting findings about what clinicians thought and struggled with. So first of all, the kind of potentially not very surprising in hindsight finding is that information that clinicians found when they did look for it and find it often affected their decision making. It could confirm decisions, or it could also often change decisions. You see this throughout a lot of studies. But the problem is that, first of all, most of these questions are pursued when the patient is still in practice, so very narrow time frame, a lot of pressure. And a lot of these questions were considered by the physicians to be highly patient-specific and non-generalizable, things that are very hard to generalize, and you need to keep thinking for each specific patient about new types of formulations. And perhaps that's part of the reason why clinicians in this high-pressure environment spend a very short time seeking information, despite the fact that they need it, despite the fact that they have these questions. And I think the finding I found the most interesting in this study is that when you take a clinician and you ask them, well, how often do you ask yourselves questions where you don't necessarily know the answer immediately? So clinicians would say, once a week I have a question where I don't really know the answer. But then you do a study and you see that for 2 out of 3 patients that they see every day, they encounter such questions. Or in another study, maybe once a week or once a month I have a question where I don't know the answer, says the clinician. But then when you actually observe them, you see 10.5 questions every half-day period where they don't know the answer. So there's a, I'll leave it to your interpretation what leads to this huge gap in the self-assessment of clinicians. And finally, there is one system I'm sure a lot of clinicians especially have heard of, called UpToDate, where you have these kind of reviews aggregated by colleagues and experts looking at the literature and trying to figure out what are the important questions, what's some important knowledge that's needed, and then feeding it into this system where you can search, and a lot of clinicians use this. So there was a nice study looking at UpToDate and outcomes in US hospitals. So what you see here on these numbers here are some sort of hospital quality metrics according to standard databases and standards. It wasn't made up by this specific study. And then when you stratify the different hospitals and you look at large hospitals, for example, or hospitals where there's a lot of teaching involved, major teaching, these kind of quality markers, you can say, you see that the gap between using UpToDate, this go-to system, versus not using it is actually pretty negligible and non-existent. So what this tells us, and reasonable interpretation, is that on the one hand, clinicians have a lot of questions for external knowledge and from the literature. They need this knowledge. On the other hand, all of these tools currently have a lot of problems in helping clinicians find the knowledge, which means that for this paradigm of evidence-based medicine to actually be effective in full force, we need a lot more work to be done to help clinicians find the latest and best evidence. And because so much of this evidence is in the form of unstructured text in the literature, so we need NLP. And I've been focusing on a few central themes, breaking it down as follows. So first is extraction, taking all this sea of unstructured text and organizing it so we can sift through it in a structured, effective manner. The second is retrieval. So how do we find information to help boost research and also decision making? Third is inference, making predictions, generating hypotheses. And finally, interaction, taking these NLP models and machinery and using them to build new exploratory interfaces for discovering the knowledge that we need. So today I'll tell you about inference. I'll tell you about two systems and models that we've been working on that use the literature, use information in the literature to predict ICU outcomes of individual patients. and also for hypothesis generation, for example, for drug repositioning. But before that, let me briefly show you some examples for extraction and interaction, or in other words, organizing and exploring the world's scientific knowledge. And I wanted to show you three recent examples that we've built. The first is extracting and exploring synergistic drug combinations in papers. The second is finding causal mechanism relationships from across biomedical literature. And finally, exploring risks and uncertainties and promising indications throughout the literature. So let me start with the first. So as I'm sure a lot of you know, drug combination therapies are of central importance in a lot of treatments. For example, in oncology, it's pretty much standard to use combinations of drugs. But the problem is that, first of all, it's a combinatorial explosion of all the potential drugs you could think of, and a lot of these combinations keep emerging, and their new combinations are studied in the literature, and we need to be able to keep track of all this knowledge so we can help clinicians keep track of the latest, best evidence. So we built an approach and a system and models for extracting drug combinations. So, for example, this is an example from an abstract in PubMed. You can see here some different treatments or drugs highlighted. And now let's focus on this part of the text that tells us that when these drugs are combined, we observe antiviral activity, which means that this drug combination is beneficial or additive or synergistic. And we want to be able to automatically extract this structured knowledge from unstructured papers. And we built an approach to do that. And then we used it to power a system for building cancer plans. So we worked together with Yossi Shammai, who's a biomedical researcher at the Technion. And they were able to find all kinds of interesting, complex cancer plans, cancer treatment plans that were not really feasible to find with existing tools. A second example is for extracting causal relationships. Okay, so again, we take papers, and now we want to extract all kinds of indications of causal relationships or potentially causal relationships. So more specifically, we look at three different types of relations. First is what we indeed call causal relations. So for example, a certain procedure results in airborne transmission, and you want to be able to automatically extract the structured knowledge from papers, so you can build, for example, a table of all these causal relationships. We extract mechanistic relations, as we call them, these kind of physical activities in the physical real world. So for example, some compound binds to some active site and can displace something else. And then finally, we have these kind of softer interactional relations where the text doesn't necessarily explicitly say how two things interact, but it does mention there is an interaction or some sort of correlation, as you can see here, for example. Okay, so we again build NLP models that are able to extract this type of knowledge from papers. And then we build a search engine. In this search engine, you can search for these kind of causal mechanisms. So I demonstrated this recently to Eran Segal, a biomedical researcher at Weizmann. So as part of one of the things that he is interested in is the glycemic responses and predicting them. So let's do that. Let's put that into our search engine. And then you can find, for example, that a certain supplement has a beneficial effect on glycemic response, or that intradermal insulin infusion has all kinds of significant effects, positive effects, again, on glycemic response, the way you perform the infusion. And other, all kinds of findings, for example, dyslipidemia has significant correlation. So this is an example of one of those interactional relations where we're not necessarily sure there's a causal relationship, but we also want to extract indications, potential signals. So we performed studies with expert hospital MDs in the States, in Seattle. And the task there was to search for causal relationships. So you're not just looking for any mention in PubMed of two things. You want to find the causal relationships, which often makes a lot of sense in the clinical setting. And for this kind of task, we find really dramatic improvements in utility and quality over just using PubMed, for example. I just want to make one final note about this, which to tie this into the kind of causal inference talks that we had earlier in this school. So Chris and Andrew, I don't know if they're, oh, it's Chris. So they presented this fascinating literature and work and ideas around causal inference. And one of the main kind of assumptions is that all the variables affecting the treatment and the outcome are assumed to be observed in your data, right? I think, was that the unconfoundedness or something? Right, okay. And of course, as we know, this is not super realistic in many, many scenarios. So one thought that that comes to mind, and I also started discussing this with Chris, is how about we can have this kind of recommender system that can kind of pool from the collective knowledge of humanity, right? All the different millions of biomedical papers out there, and suggest potential other causal factors that you may have not included in your analysis. So taking from the external world to enrich your internal representation, potentially finding a lot of confounders and making the unconfoundedness assumption more realistic. And then maybe there's a human in the loop there saying, yeah, this is relevant, this isn't, and I do have data for this, I don't have data for that, and kind of building a system. So that's something interesting to think about. Finally, and I'll pause for questions after this segment, another way for, another view of the literature that's also very important in research and in clinical decision making is identifying challenges, risks, areas where we don't necessarily have a lot of knowledge, and also all kinds of early promising indications or hypotheses that are worth pursuing. So we want to be able to extract all this kind of knowledge. So here are two examples. For example, this is a kind of hypothesis or a kind of early indication that the RBD of SARS-CoV-2, I guess, S protein, may serve as a better candidate for developing vaccines. But then you also have a challenge later on that vaccination has potential, may be confounded by many different factors. So these are just two examples of hypotheses and challenges out of many, many, obviously, that are out there in the literature. So we want to be able to build a search engine that can help us find these things, where you can input the topics or keywords you care about, and then find the problems, limitations, or directions and hypotheses. So one example you can think about for motivation is, let's say you are a biomedical researcher, and you want to ask, what don't we know about the ACE2 receptor in COVID-19? What are some interesting directions at the edge of science around this very well-studied combination of topics? So when you go to PubMed and you search for COVID-19, the ACE2 receptor, obviously you're going to retrieve a lot of known knowledge about these things because they're right at the heart of the mechanism of COVID-19. So there's a lot of kind of obvious or well-known statements. But then you can go to our search engine, which helps you find these kind of fringe, or let's say things at the edge of science, the emerging questions and uncertainties and hypotheses. And then one of the things, for example, we could find, I don't know if this is by now well known, but dates back to late 21. And you can see, for example, a potential hypothesis that there may be a role for the ACE2 receptor in pathogenesis of liver damage in COVID-19 patients. So again, we gave our search engine to MDs with extensive research experience, and for this type of knowledge task, find higher utility and quality than what they were able to find with PubMed. Okay, so before I move on to the next part of this talk, which is more about predictive models using the literature, Are there any questions at this stage?
Is this, you started with the challenge of helping I got this mental image of this worked out physician with all, seeing a lot of patients. Does this really meet that, have we reached the state where really, this kind of search?
Or this is a big challenge, so no, I would not be so presumptuous. What, for example, you see, again, in these studies, like this one or the one with the causal relationship, is that if they go to the go-to tool, PubMed, and they want to find, for example, risks for a specific drug in a specific type of cohort, or they want to find all the causal outcomes or potential causal factors for a specific disease. Using our approach, they're able to do this much more easily and report much better results and experiences than with PubMed. So it's kind of making progress toward that. And in the second part of the talk, I'll show other tasks and other ways in which we can find literature for specific patients. So all in all, we're making gradual progress across a lot of different, but very far from
so I think the thing is that it's very hard to translate, percent improvement in terms of questionnaire to what it actually means to the physician doing those things. At least for me, it's very
right. I mean, I like that study based on UpToDate, right? That when looked at the use of UpToDate, again, trying to stratify by different hospitals, and then the metric was actual direct outcomes on the hospital treatment and on outcomes in terms of all kinds of well accepted metrics of interesting to perform that kind of study also based on these information tools, so linking information seeking to actual outcomes.
But then you might be worried that it's all about some confounding variables such as
yes. Absolutely. So that's why, we need we need like an RCT, for example. I think would be is something I'd love to do. I have all kinds of thoughts about RCT, and they have been done with information tools, right? So the same hospital, same kind of cohort. Some physicians have a specific information feature or function or tool, and the others don't, randomly, and seeing where the patient outcome actually is improved.
Question. So you gave us the bottom line, but I'm trying to understand if the typical answer is, I don't know, you find a specific sentence in one abstract that's does it, or does it integrate I don't know, information from multiple vague statements in many abstracts?
Yeah, so that's an important question. So we find these statements across all papers or abstracts, right? But I think you were asking about whether we just show a list of all these things, or whether we kind of combine them into some sort of more general statement. So the answer to that is that mostly not currently. Mostly currently we segment by topics. You can see all the challenges in a specific topic, which can be very, very specific as you want it to be. But still, you'll see an individual list of sentences. For causal relations, we can do basic aggregations. So you can build a table telling you if 20 different papers said that this drug has some causal specific causal outcome, or 50 different papers say that this disease has some correlation with some other comorbidity, right? So that's fairly simple to do with our tools at the moment. But there's a lot of work on how do you take this to be done, about how you take this diverse, as you're saying, vague scientific language and identify when two statements are actually referring to the same thing. So this is actively something that we're pursuing. It's a big challenge in NLP generally, not only in this problem. Okay, I think I'll move on to the next.
Can I,
Yeah, of course.
we're trying to get to the last questions, but
Yeah.
how good are those machines at realizing that at the end of the abstract is something that says that this this is not true. Like our hypothesis was that X influences Y, and we did this and this and this, and the conclusion is this is not the case. So, that's kind of thing fools.
So let me put it this way. In general, NLP approaches for such complex texts can be fooled in many different ways, and with all these very complicated hedges and specific cases, yes, they will be fooled. NLP is getting better, and it can in many cases capture the more simple variants of what you're saying. The problem is that language is so diverse, there can be many different ways to say that, and it fails at the richer cases. I'll actually mention something related to that, negations, and as part of this talk. It's an important NLP test, also in the clinical setting, where with physician notes, where physicians say patient does not have something, right? And you want to be able to capture that. So there's a lot of work to be done to improve NLP there too. But we're trying to explore what can we do with our current existing state-of-the-art machine. Yeah.
In the first day in the introduction session, we were talking about traditional NLP versus ChatGPT language models and
Okay.
state-of-the-art. So could we have just a general idea of what kind of technologies we use for these kind of tasks? Was it more language modeling?
Yeah, it's only language, but not ChatGPT scale language model. For multiple reasons. Obviously, first of all, a lot of this work was done before the latest version of GPT-3, which is indeed a kind of a dramatic improvement. I think, but more importantly, is the scale of the literature does not necessarily align well with the current mode of working with these models that are behind these kind of paywalls, and at the scale that you need, quickly explodes. And I guess an even more fundamental challenge would be, as you'll see, I'm going to now talk about using not only text in the literature, but text in clinical notes. So what do we just send clinical notes out to some external vendor? And obviously we cannot do that, right? So, and currently that's how people work with ChatGPT and all these things, is via a cloud service, right? So that's currently not possible, but I expect, it's very reasonable to expect that these things will be soon also open sourced, all kinds of different versions, maybe not exactly with the same performance, and then certain players will be able to have these deployed like on-premise, and then maybe we will be able to use that kind of technology.
So what model did you use?
Sorry?
What model did you use here?
Yeah, so a lot of different language models, right? So all kinds of.
Robert, I don't know.
Yeah, I mean, it's a kind of second or third order question actually, but pre-trained language models of the BERT and Roberta variants, trained on PubMed, trained on clinical. It depends on the use case, but usually you just try a few and you see what works best, right? So, yeah. Okay, any more questions? Okay, so let me move on to predictive models, and I'll start with our work on literature-augmented clinical outcome prediction. This was led with a former intern, Akanksha, worked with me. And let's go back to our discussion about evidence-based medicine. And let's focus on this intersection, right, of what clinicians know, the kind of internal representation of clinicians' experiences and knowledge, and what the external knowledge is in the literature. So as a very, very coarse approximation of clinical decision making, mostly for illustration purposes, you can think of a physician trying to, looking at some patients' EHRs and trying to identify whether the patient is at risk for something. So the patient will, physician will retrieve from their, so to speak, internal knowledge and experiences, relevant knowledge for making this decision or for answering this question. And in these complex cases, or cases where the physician maybe needs to complement their internal knowledge, they will go to external knowledge sources like UpToDate and PubMed and try to find more knowledge to either confirm their hypothesis or maybe change their decision. And then they can synthesize these two sources into a prediction, right? Essentially, these decisions are predictions, as we well know. Now, sorry. Yeah, so we want to be able to introduce some automation into the second part, into the external knowledge retrieval to help make predictions and to help support clinical decisions. That's the kind of overall general vision. And I'll present some progress. So I'll first discuss prediction of clinical outcomes in ICU patients by retrieving patient-specific medical literature. So for each patient, we're going to find the relevant literature in PubMed, and then we are going to use that knowledge from PubMed combined with the internal hospital data to improve predictions. So specifically, we use the MIMIC dataset. I'm sure most, if not all of you have heard of. Has anyone, who's heard of this dataset, MIMIC? Yeah, okay, so get a pretty good guess. But basically, in MIMIC you have, for ICU patients, you have, for example, their admission note when they come in. You can see all the different attributes that we have there. And then you can kind of roll forward into the future, look at the discharge note, see the outcomes. So for example, this patient was not deceased at the end of the ICU, and they had a pretty long length of stay of over 14 days. So we can take these outcomes and treat them as training signal supervision for training models that attempt to predict these things. And specifically in our work that I'm going to show, we're looking at the admission notes only. So it's a form of early stage prediction, because obviously during the ICU there's a lot of knowledge gathered incrementally and temporally, and most work looks at making these predictions kind of on a rolling basis based on more and more knowledge. Here we are in a kind of harder setting, looking only at the admission note and trying to predict into the future. Now, state-of-the-art models in this area predict outcomes from internal data only. For example, models are relevant to what I'll show. They take the patient notes, as you can see here, right? And these patient notes actually have a lot of the structured data inside them, right? I mean, it's not just text, it's a lot of numeric values, like from labs, results, etc. And they take these patient notes and try to predict the outcomes by training machine learning models. And here we ask if we can improve the performance by leveraging external knowledge that's patient-specific, finding the evidence, so to speak, automatically to help make better predictions. So to do this, we build a system which we call BEEP, for Biomedical Evidence Enhanced Predictions. And here's a real example from our data that also helps show what's going on. So a patient comes in, we have their admission note. The patient is a 49-year-old male with refractory hyperglycemia, type 1 diabetes. So then our system finds literature that's relevant to this specific patient in the context of the specific outcome we're interested in. For example, risk of mortality during the ICU hospitalization. And then we see, for example, a specific paper that says that for severe hypoglycemia in adults with type 1 diabetes, there's actually no increased risk of mortality according to this study. So when we kind of hide the literature aspect and we only use the kind of state-of-the-art approaches that look at the admission note, the model actually predicted, in this case, made the wrong prediction, that the patient is going to die during the ICU. By integrating the kind of, let's call it, more well-established causal knowledge from the external community, or in other words, from medical studies, in this case, the model was able to make an accurate prediction, integrating this knowledge into the model to predict patient survival. And I'll show some more examples like this later. So to build BEEP, yeah. By the way, there's also the crackling here. I hope everyone can hear me all right. Yeah.
It's okay to start?
Yeah.
So, I have one problem. This is amazing. It's very helpful. sure, but the one thing
I'm not so sure, but okay.
you enter bias into the system when you just check for papers that are relevant to your use case as you described it. Because the paper themselves, in computer science papers, you can find many articles that completely contradict each other. And they're both with code, both with empirical results, and they still say exactly the opposite.
Yep.
How do you...
And in medical papers, the same
Of
thing.
course, but
Yeah.
I have experience only with that kind of papers. So how do you deal with this in this case? Like, you get the result that it won't increase the chance of mortality, but maybe there is another paper that says the exact other way.
Yeah. So yeah, it's a great important question. The simple answer is that, as I'll show, our models kind of learn from the outcome signal. They learn how to average together the information from multiple papers. So the model, in theory, will have the ability to take in contradictory literature, have some information about what each type of study did and the knowledge there, and then reweight this evidence accordingly to what will lead to the most accurate prediction. That's in theory, that's what we currently do. But you're completely right, and we don't actually, in this paper, explicitly try to control for contradictions. We're now going to work on, first, the ability to detect contradictions. So there's one project like that ongoing. We want to be able to use NLP to detect contradictions, not an easy task. And then, given that, maybe the model will have some better what we call inductive bias that we can integrate into it to look for contradictions more explicitly. So it's something to work on. Yeah.
One notation of a contradiction and evaluating. You can't evaluate it based on count. Like one research team could.
Based on what? Sorry.
On count of that many papers said that, and one paper says opposite.
Yeah, you're right.
And like one team could release 3
Yes.
papers about this is like that, and the other team might
Yeah.
be the actually correct one.
Yes,
saying the
right.
opposite. So it's
Right,
a
so-
really
so-
complex problem.
Oh yeah, sure. So what you're saying, in other words, is that we also need to look probably at some sort of signal of rigor of a paper or soundedness. So there's a task of trying to automatically measure the soundedness of a study. Easiest signal, the sample size, right? So you can imagine appending to each paper the sample size used in the study to kind of guide the model to focus on that. Obviously, it's not enough, and there's all kinds of other metrics. But again, I'm combining here the kind of the simple answers to what can readily be done, and then acknowledging that it's a big challenge. Both of your questions actually touch on big challenges in integrating and measuring the utility of information in the literature, which is very variable and diverse. Okay, so to build BEEP, our Biomedical Evidence Enhanced Prediction, we need an ability first to retrieve patient-relevant literature. So we take the patient chart, and we want to use information retrieval or search technology that finds medical studies relevant to each specific patient. In a kind of nutshell, one kind of conceptual thing to note here, which is very different than what you probably think of when you hear the word search, is that we're veering away from this kind of standard way of search where the physician needs to think of what are the exact keywords I need to search for, and how do I phrase this, and what are the important aspects of the patient for my specific question or outcome, and then go to PubMed and do that. No, so what we're saying is the patient is the query, right? We take the full information or representation of a patient, all of their different background and current presentations, etc. And we want to be able to learn automatically what's the information that's relevant in this very complex object that is a patient, what's the relevant information for answering a specific question without having the physician try and predefine it, which is not only inefficient but also suffers from many biases and limitations. So we do this with two different technologies, let's say. The first is extracting key patient entities using these inductive biases, or something that we know is probably important in the clinical setting. So we focus on extracting problems, treatments, and tests. So you can see some examples, sorry, you can see some examples here of problems, treatments, and tests. And then we link them to MESH. I'm sure most of you have heard of this, this ontology of medical terms. We filter for negations, like we were saying, right? So someone has no headache, so we don't want to search for papers about headaches. And then we use the MESH entities as queries to PubMed, right? So PubMed has an API for searching by MESH terms, so we can use the MESH terms linked to each patient to perform the search. And the second type of technology is these neural language models, like you asked, where we train models, and I won't go into all the details, to map the patient, this complex patient object into some neural embedding space or vector space where patients are similar or close to medical studies that are relevant to them. I can answer more questions about this part later if someone's interested. So given that we have the relevant abstracts for each specific patient, now we want to aggregate these abstracts into an outcome prediction. So let's say we have 10 abstracts from PubMed for each specific patient. We now will take a language model that, so to speak, reads those 10 papers and reads the internal clinical data and integrates that into an outcome prediction. So as a simple example of how this is done, for example, we learn a weighted average of the top 10 papers in a way that maximizes predictive accuracy. That relates also to your question, right? So we can assign different weights to different types of sources of evidence and train the model to identify how to reweight the evidence in a way that maximizes predictive accuracy. And then we can take the literature representation and the EHR representation, for example, just concatenate these two things and feed that into an outcome classifier. Okay, so again, working over the MIMIC data, we have 3 cohorts that we looked into here, and the reason for these 3, or just because a lot of papers focus on them, so we use them as baselines, but nothing I'm presenting here is, at least in principle, tailored for these 3. So in hospital mortality, big cohort, prolonged mechanical ventilation, or PMV, slightly smaller cohort, and then we have length of hospital stay, which is a 4-class target variable. Okay, so in terms of results, we first see that there's a pretty large boost in area under the curve, or F1, over the state-of-the-art that uses only the internal clinical notes. For example, for predicting prolonged mechanical ventilation, which, as far as I know, and I'd be interested to hear feedback from people who are more knowledgeable on hospital settings. As far as I know, it could be important for resource allocation and planning in a dynamic fashion. For example, I think in COVID that was pretty important. But then we look at the interesting and potentially more realistic scenario where we want to raise alerts only for high confidence cases to avoid what's known as alert fatigue, which is very important in clinical settings. So we don't want to keep sounding the alarm more and more. We only want to do that if our literature-based model is very confident. So we look at the top 10%, the top 15% of predictions, the ones that have the highest confidence. And now we're going to look at these high confidence predictions with our model and with the previous state-of-the-art. And here we see really big boosts over the state-of-the-art. So for example, for PMV, prolonged mechanical ventilation, we see a 9-point increase in precision and a 2-point increase in recall over the state-of-the-art when it's also measured at the top 10 or 15%. And for mortality prediction, we see a 27-point increase in precision of the positive class, right, of predicting mortality risk with a relatively small drop in recall. So finally, we also perform a qualitative analysis. So we sample 200 or so patients, and then we look for the cases where the literature substantially increased the model confidence in the right direction, right? So you can assume having the previous state of the art and looking at its model confidence and looking at what the true outcome actually was. And then we're looking for the cases where adding the literature adds the big delta, increasing the confidence in the right direction. So actually the example I showed you earlier was one of these cases where the literature substantially moved the confidence in the direction of the right label and flipped it from wrong to right. And here are just two more examples in the interest of time from our paper. So this patient has cirrhosis, and we retrieve a paper that says that cirrhosis patients, when they require mechanical ventilation, they tend to die in the first 48 hours of intubation, at least in this study. I don't know if this holds across all your experiences in hospitals. So what does this tell us in a kind of basic logical reasoning or inference that the language model was able to do? It tells us that if you have cirrhosis and if you underwent mechanical ventilation, you likely will not need prolonged mechanical ventilation because you would likely be deceased. Second example, so we have a patient, type A aortic dissection, and they underwent surgery. And then we find a paper that tells us that with type A aortic dissections, with patients that undergo surgery, when you look at in-hospital mortality, you see that there's a list of factors that are particularly predictive of in-hospital mortality. So you can see them here. CPB time, diabetes, and post-operative bleeding. But this patient didn't have any of those in their clinical note. So this is a kind of evidence type where the known outcome indicators for mortality are not present in the patient's note. So the model, again, was often able to make this kind of fairly basic inference that combines this fact that the patient doesn't have the known indicators to decrease the likelihood of a certain outcome. Okay, so I'll pause here for any questions about this part, or I can move on to the last part. I think we have about 12 minutes. Okay, so let me move on to, and by the way, the code is open source, etc., and the part of the data that can be open source, which is the PubMed papers linked to each patient ID and MIMIC, that's also open on our GitHub. Okay, I'll move on to the last part, which is biomedical knowledge-based completion, or in other words, biomedical hypothesis generation, working with knowledge graphs. And this was led by former intern Raul. Okay, we want to be able to predict links in biomedical knowledge graphs. For example, predicting drug targets, predicting repositioning of drugs, predicting side effects of compounds, etc., etc. And we, just to illustrate, we worked in this study with 3 different knowledge bases that are related directly to clinical questions around drug discovery. So one data set from Harvard researchers is a collection of drug disease pairs that's intended for drug repurposing research, finding off-label uses of drugs. Another recent data set published in Nature, multi-scale interactomy, is a bit lower level, right? It focuses on diseases, proteins, genes, all kinds of other biological entities and functions. And then finally, there's a knowledge graph that has a bit more of a clinical bent, looking also at side effects and symptoms. So we want to predict links, new links in these graphs, and as a kind of very basic introduction to link prediction in knowledge graphs, So you can think of these kind of structured queries that we feed into our model. So for example, in this illustration, we want to find or predict all the all the diseases that could be treated by aspirin. Of course, it's just for illustration purposes. So we will feed in this query into the link prediction model and then get as output a ranked list of all the different diseases ranked by likelihood of being treated by aspirin. Now, the kind of standard prevailing way to do knowledge graph link prediction is via these embeddings that I think you've all seen by now. We will learn vector representations of the entities like aspirin and fever, and we will also learn representations of the relationships we're interested in, like treatment. And then we will integrate those vector representations into some score that can be used for ranking all the different candidates, all the different diseases. And these types of models are typically based on the graph structure, right? So you look at the neighbors of a specific drug or a specific disease, and you use the information propagated across the graph to make better predictions. But a key problem of those methods is that by being based on the graph structure, they haven't got a natural ability for integrating rich, unstructured knowledge, for example, from the literature or from rich descriptions of, say, drugs in the drug bank knowledge base. So we want to be able to also integrate rich textual information. So just like general NLP trends, year 2 there is an approach that uses language models. So you take the text of these different entities and you combine them into a transformer language model to output this ranking score of all the different candidates. And it's also related, I think, to your question about what language models we use, right? So there's a class of language models that was trained on biomedical literature. So you have SciBird, BioBird, PubMedBird, a few more have come out since then. And these language models have, so to speak, read millions of biomedical papers, and we want to see if we can tap into their latent knowledge to generate biomedical hypotheses. So we study the ability of these language models and of the graph-based models, and across those 3 knowledge bases that we use, we see that they kind of perform differently on different subsets of the data. On some subsets, the knowledge, the graph-based, the structure-based approach does better. Other subsets, the text or language-based approach does better. So this suggests potentially that they may have complementary strengths, and we may want to explore combining these 2 different modalities. So that's what we do. We call this cross-modal link prediction. So we look at those structural graph-based embeddings. We look at the language-based representations, and then we reweight or re-rank the graph scores by using a transformer language model. So you can just think of this as a simple type of ensemble where you reweight the graph and the text information into a final prediction. And this integration, simple integration of text and graph information, provides a very substantial improvement in terms of all kinds of ranking metrics I'm not going to go into, over all kinds of state-of-the-art approaches, right? You can see Roberta again for the US and all kinds of other models. And this type of integration of text and graph information leads to really substantial improvements. One final note on a more technical but important level is that these language models are pretty big and heavy creatures, right? So you asked about GPT-3 and all these billions of parameters. And if you want to take knowledge graphs at a real large scale, a realistic scale, and take all the potential drugs and all the potential diseases and their textual descriptions and all the potential combinations of these things and feed this over and over again into a language model, you're going to get a combinatorial explosion. It's going to be very, very slow. So we just took one small subset of Wikipedia just for a technical illustration, and with with efficient graph approaches, it can take a few seconds to quickly rank all the candidates, but 11 days with a pretty small language model. So it's not a scalable approach to use the language models currently for large-scale hypothesis generation on big biomedical knowledge graphs. So we built an approach, which I'm not going to discuss in detail, that learns how to progressively pass sets that are smaller and smaller from the efficient graph-based models all the way down to the most expensive language models. So our approach learns which examples should be transferred on from the, let's say, simpler graph-based approaches and transferred and propagated down this funnel to the expensive language models using the textual information. Happy to answer more about that probably offline. And as a final result here, so we evaluated all kinds of knowledge bases, for example, on ReproDB, the drug repositioning task. We also improved state-of-the-art accuracy by a few points, which is substantial. At the same time, we improved efficiency by at least one order of magnitude over the most competitive ensembles that combine the graph and the text. So that's an improvement on both fronts. Okay, so to conclude, I presented today some of our work on biomedical search engines, on hypothesis generation, and on using the literature for making clinical predictions on patients. Tying this into the more general themes and long-standing problems that need to be explored of extracting structured knowledge, of retrieving information, of using retrieved information for inference and reasoning, and how do we make all this accessible in human-friendly visual and interactive systems. And this is all ties back into the goal of helping researchers and clinicians throughout their diverse tasks, helping them find the knowledge they need and synthesizing it to help them with specific tasks and specific questions. And with that, I'm happy to take any remaining questions.
So we have time for 2-3 questions.
Yep.
Is it possible to take embeddings from the text and put it in the graph? The opposite point.
So I'm not exactly sure what you're asking, but let me say that yes, I mean it's all about the representation of nodes and how you integrate the text and the graph. I mean, in a sense, we are doing that, right? I mean, we're taking the graph representation, we're taking a text representation, and for each specific entity, we are merging them. But there are all kinds of approaches, for example, graph neural network-based approaches that will initialize the node representation with some embedding of the text. So those approaches tend to be not effective currently and much less efficient. But in theory, yes, and probably you can, someone will get it to work more effectively, and then you can kind of directly fine-tune the language model representation together with the graph for link prediction. Yeah. Any more questions? Okay.
Thank you, Tom.
Thank you.
So I appear in the program between you and the break. Since it's an hour and a half, I'll try to do a quick half an hour lesson, and then we'll take a break. And then it will be something that is more of a lecture on findings. So. I'm going to do something dramatic and use the board. I hope you don't mind. Is this on? Okay, now it's on. Hopefully it's, and since I'm using the board, we can go in multiple directions. So I want to touch on 3 subjects. One is very, very wide, and it's the question of screening for disease, which is, so I'll just give some ideas on relevant places for AI, and then I'll tell you a bit about liquid biopsies, and in the last part I'll give you a talk about our favorite brand of liquid biopsy, which is called cell-free chip. And so hopefully it will tie all of the from zoom out, we'll zoom in into specific results. So let's start with the question of screening. Anybody know the difference between a screening test and a diagnostic test? Intuition? Zach?
Perhaps where you are on the curve of prior probability and evidence.
Okay, so I like the use of the word prior and probability. Yeah.
So just to say, diagnostic is when you've reached some arbitrary threshold of where, from a cost, risk, frightening the patient perspective, it's worth doing this extra step. Whereas screening, it's being typically done on a larger population.
Okay.
And the prior probability is therefore never.
Yeah, no, so you're going,
Yeah.
I don't know why the microphone.
Yeah,
It's working, it's working.
No, but it has bubbles.
Yeah,
So one definition, and I think we can, I agree with what Zach said, but I'm going to simplify it a bit in order to make our discussion, is that if we look at the progression of a disease, so the disease become worse with time, we can look at this graph of essentially where the x-axis is symptoms. And at least initially, if it's, for example, a cancer, we don't have any symptoms, and eventually it goes up and becomes something that the patient is sitting at the doctor's office and say, I won't go away until you tell me, until you fix me. And somewhere in between, there is a threshold where at this end of the spectrum, we have symptoms, we have to diagnose why the patient is having those symptoms. And somewhere, and again, this is a murky region, but somewhere on the left here is we have a population that is asymptomatic, and we want to find out if they have the disease before it becomes symptomatic. Okay, and again, this is a very arbitrary, so here we are screening, and here we are diagnosing. So the kind of idea of a screen is that you go to do your yearly checkup, and the doctor tells you, because you belong to a certain population, I recommend these tests that you will do, and if everything is fine, you continue with your life, and if the tests come up with some kind of finding, then we need to worry about what to do next. Okay, but the prior probability is that you're healthy. Isn't that mostly you're healthy? I don't think I need to explain to you that catching diseases, especially, again, I use cancer as the running example, though it's not the only disease in the world, but cancer in particular, your odds of surviving are improved the earlier we catch it. This is actually sounded to me a year ago, 2 years ago, as obvious, and I see Zach is shaking his hand. There are only 4 types of cancer for which we have medically proven trials that show that finding it earlier is
actually improving your probability of survival. Anybody knows who they are? Which types?
Breast, colorectal,
Lung? Not so sure about lung.
Lung is,
lung, well, when you get to very early stage.
So far, all we know is that if you find it early, for sure, you're going to live longer with it,
yeah.
but your lifetime may be the same.
Yeah, so there is the question how long you know that you have the cancer versus whether you live longer because of that knowledge. So prostate, breast, and colorectal are definitely ones where early intervention is improving and extending life. Lung is the one that there's arguments about. And that's where we stand. So for example, pancreatic cancer is we all talk about the need to diagnose it, but if you talk to the medical, it's clearly a good idea to be able to find early pancreatic cancer so we can learn maybe what we can do. But right now we don't know, unless it's a resectable, which is not necessarily common, we don't know how to help the patient. Yeah, question?
But it sounds that there is some bias because all these cancers are the ones with a screening test. So maybe the other one is much difficult to research to answer this question.
Okay.
And always ask yourself, who's getting paid?
Yeah. So
Seriously.
for those who did, I think I should park a mic with Zach, and so you can hear him as well.
Yeah.
So there's a monetary incentive for the system, and then there is the chicken and egg that if you can't diagnose it early, you cannot prove that you can do something about it. So, but let's talk for a second about the process. So you have, assuming that we do want to find things early, we have the general population. And we want to test for a disease. Usually we do not, those tests don't come for free. And so usually we select a subpopulation for testing. For example, colorectal cancer, depending on where you live, it's around 50 is the kind of threshold for starting to get notes from your doctor about different ways of getting tested. I see young people doing yes with their head, which is surprising, but okay. So that only above a certain threshold. So there is a subpopulation. Let's use a different. Do we have blue? Yeah. So there is a subpopulation that we don't have blue. Okay. There is a subpopulation that we decide based on our knowledge, usually from epidemiological studies, that we are going to screen. Ideally, and then there is a population of people who actually have the disease, but we don't know that they have the disease. Okay? Ideally, the intersection would not be empty. And even better if the intersection, if these people have more of the disease than these people, or the other way around. Okay, but real life is somewhere like this. So this is disease. And maybe it's smaller. Nothing is to scale, but okay, and this is screened population. Okay? So there are people who are younger than 50 years old that have, unfortunately, colorectal cancer. So they don't reach the screening that we recommend. And there are many people above 50 years old that do not have colorectal cancer. Hopefully everybody here in the audience above 50 at least. So we're going to do our test, screening test, and it's going to essentially divide this group into two groups, right? Positive and negative finding. So it's either positive or negative. What's the ideal test we should have? This is not a hard, tricky question. Ideally, we would like to at least have all of these people as positive and everybody else as negative, right? But as luck has it, we have certain amount of errors. So let's put here on the side a quick discussion about errors of tests. So this is cancer minus plus, and this is test. I know I'm starting simple. Hopefully it will get more interesting quickly. So these are true negatives, these are true positives, these are false negatives, and these are false positives. And clearly we want these two to be small, and there are different names for the things we can look at. We can do specificity, sensitivity, which have to do with when I say out of the, so specificity is essentially true positive out of the false negative plus true positive, and so this is specificity. Sorry, sensitivity. Specificity is essentially is how much of the is in this direction. True positive out of. Sorry, I keep flipping those. Okay, one is specificity, one is sensitivity, and I now confused myself. So let's.
Every brilliant statistician I've ever known admits privately they have to reduce for themselves
Yeah.
2 by 2.
Yeah.
So the young
That's-
people should not get embarrassed if you forget what sensitivity is, but just do
Yeah.
2 by 2.
So sensitivity is essentially if there is a disease, what's the probability of catching it? So it's this. And specificity is if I catch something, how many of them are real disease? So it's this term. Okay? And most of the tests we will do will have fairly high number in both of those areas. Let's say 99% sensitivity, specificity. Is that good enough for us when we screen the population?
The whole population, then no.
Or this subpopulation?
Maybe.
Okay, but what is missing for
The prevalence of the disease.
the abundance of the disease, because usually this group is much smaller than this group. And so what people talk about is positive predictive values, which essentially is asking.
What you did on the right, that's a positive.
Yeah, so I wrote the positive predictive value instead of the, yeah. Okay, so this is PPV, and negative predictive value is true negative versus the predictions of negative. But usually what we kind of interested in is positive predictive value. What fraction of the people who will get bad results from the screening actually have the disease? And so if we think of those terms, hopefully the disease is not too prevalent. And so even if it's very specific, the positive predictive value is not going to be amazing. Okay?
Why practically do we care more about PPV than negative?
In a second, yeah. That's a great question. I'll try to answer. So let's continue the story. These people, they are predicted to be positive, and some of them are really positive, right? And then there is a group, another group, which hopefully is larger, and that has some amount of red inside. These we send home and say everything's okay. And now comes essentially the trade-off between the two types of errors, and that depends on what we do here. For example, in the example of colorectal cancer, we're going from here to another, essentially to a confirmation. So colonoscopy, from our perspective, is almost perfect way of discovering colorectal cancer, okay? Except for suffering it, but in terms of its ability to detect it, it's very good, okay? So all of those people will be sent to colonoscopy, okay? If we're talking about colon cancer. All of these people will be sent home. So in this example, the amount of people who sent to colonoscopy translates, Zach said, money, translates to a lot of money. You need a team of 3 people, specialized equipment, and a whole bunch of things in order to do one test. So this is an expensive, resource-intensive endeavor. These people, and again, assuming that our test is not, doesn't have a systematic blind spot, which is a wrong assumption always, but nonetheless, since colorectal cancer is usually relatively slow, these people will have another go of it the next time we do the screening, okay? If it was a cancer that, pancreatic cancer that blooms within half a year, then essentially these people are doomed. They lost their chance for early detection and the benefits it comes with. Okay? So the answer to your question is essentially what is the cost of having to detect the cancer at 1 year or 5 years later versus the cost of sending a lot of quote unquote healthy people to get negative colonoscopy results. And one of the reasons we screen not much of the population with colonoscopy is because it's so expensive. Okay?
What's the cost, like financially, the cost of
Mis-screening?
Of missing a colonoscopy, like on the healthcare system, etc.
Of these guys.
Yeah.
So again, it depends on if it's a very slow thing, it will take years to develop, and you'll see it in the next round. And then you'll do a colonoscopy and you remove it, and that would be the cost. If it's very fast moving, it might be that now you have somebody discovered in advanced stage of cancer and you need complicated surgery and treatment and disabilities and many unpleasant things. Okay? Everybody on the same page? So
I just want to say, dying is actually cheap.
Yeah.
It actually saves money. In fact, the smoking company, Philip Morris, once sold an analysis to the Czech government proving that if people smoke, healthcare costs will go down because they'll have a fast exit with lung cancer as opposed to slow exit.
Yeah. With this happy note, we can suggest more effective ways of doing it, but
we can also smoking.
So when we talk about screening, we really have to be aware of the prevalence in the population, the ability to detect the population that really needs to undergo screening, the cost of the screening, the precision and specificity and sensitivity of the screening. And then another question is whether you have a confirmatory assay and how expensive it is. For example, early detection of pancreatic cancer, we come back to that. We don't have a good test, and to confirm it, you have to do a very dangerous procedure because doing biopsy of the pancreas, again, I don't know the details, but it's not something that you do without thinking. It's like colonoscopy. Okay? So you get this news and then you don't know what to do with it. You don't know whether to go for treatment or not, and whether you're really sick or it's just something that looks on imaging not so great and might be there. Okay, so do imaging and it's not decisive and so on. Okay? So one of the questions that we have to think about is whether we can get confirming results and how hard it will be to do, because if this is really expensive, then you want this group to be very small. Okay, so there are multiple parameters that go into the game, and probably I didn't list all of them, but I want to first to make you aware of the space we're living in, because it's a complicated space. Now, there is another group of patients that undergo this trip. Again, we're living let's stay with colon cancer as a running example. And these are people that have very high probability of getting colon cancer. For example, family history, or they had it in the past and are considered cured, but there's some chance that it will return. Okay? There, the amount of red inside the group that we are testing is much higher. Okay? And there it might be that we have totally different situations. Okay. So this kind of picture is the classical picture that we give when you talk about public health decision about, the Israeli, we have this committee that decides on healthcare spending and decides who should get what and when and so on. That's the kind of decisions that they take into account, hopefully, when they go and make the guidelines for the next few years. Okay? But the thing, and this is returning to things we talked about on Monday, is that we know a lot about every one of those people in the population. I mentioned risk factors that are known, but there might be many other factors that will make our prior probability of having the disease different. Like we talked about blood tests and decrease in, what was it, iron or something like that over time. As in, Amos, you haven't mentioned it yesterday, as one of the indicators of colon cancer. That's something that we currently do not really take seriously when we stratify people. So one place where AI, I think, and this connects with what we heard from Dan Turner on Monday and from Amos yesterday, about the fact that we have a lot of information about the patient and how can we stratify this population into groups for which we can make different decisions because we have different prior information. Okay? The test is still the same test, but the prior information is different. And so, do I need to write Bayes' rule or?
I think it's good to write. Why not?
All right.
Okay.
By the way, one of my students, just so you don't feel bad, one of my students who's clinical grad, there was a study where we asked, 35 years ago, doctors at Harvard asked a simple prior PPV question. Here's the prevalence of disease, here's sensitivity, specificity, positive test, what's the answer? What's the likelihood of the test? And and the right answer was 2%. And back 35 years ago, a New England Journal article reported that half of the Harvard doctors reported the correct answer, and half of them said 90%. Because they don't do it, human beings don't do Bayes' rule naturally. And the amusing part of it is my student asked the next generation of Harvard doctors the exact same question 35 years later, with the exact same results. And unfortunately, New England Journal doesn't publish the same paper twice, so we were only able to publish it in Annals of Internal Medicine. It's called Medicine's Problematic Relationship with Math.
Yes.
It's very unfair because all humans are actually pretty bad with Bayes' rule. This is the problem, because this is why.
Okay, so the B rule
Yeah.
is that the probability of having the disease given that the test is positive is equal to the probability of getting a positive test given your disease status, which is what I erased just now, times the prior probability of the disease over the probability of just getting positive results. Either this is sum of this term for the two disease states. Now the more interesting real life situation is the probability of disease giving the test and X, which X is any other information we have about the patient, that hopefully the test itself doesn't care about whether you ate aspirin the last 4 years in a row or what was your blood measurement, but the probability of the disease might change, so we care about essentially what's the probability of the test being positive given the disease, and your prior about the disease given X, and so on. So this is where one place where AI or building better models can change a lot our ability to decide, A, how to interpret results, and B, people with sufficiently high prior should be tested more often or give it and so on. And I think that's more or less what I wanted to say about this subject. Questions about screening and why we care about numbers and Bayes rule screening? Yes?
Just maybe an anecdote. So in the UK we have a national screening program in breast cancer for women over a certain age are given automatically offered a mammogram, and there's an AI award into the NHS, about 140 million, to actually bring AI into the National Health Service, and one of the things was about introducing risk profiling. And it's interesting because the political angle was that they're worried about that it's seen that you're withholding screening. Rather than, so if you start to risk stratify, then they're worried that people who aren't offered see it as a kind of...
So you have to be politically smart and always use the certification to offer people who currently do not get the testing and offer to get the test.
It's hugely political, because in Switzerland, in America, it's as early as 40 years of age for everybody, partly because all the radiologists are pushing for it because they're getting hundreds of millions of dollars. In Switzerland, they've done the evidence, and it's basically they don't offer it for anybody under 50, so it's very repetitive.
So you do not condition the treatment, the test outcome based on X.
So I said that I assume that
whatever. Is it actually? I mean, like certain people have different.
All assumptions are wrong.
But how wrong is it?
I think it's reasonable in this case. Okay, I will try to push forward a bit. Okay. So one of the reasons that screening is not great, I mean, ideally we'll have just great screening method, and these groups will be just the red, and we won't have this big argument, and they should be really cheap, but we don't have those things. So we have things like PSA, which is a blood measurement that is predictive for prostate cancer. I don't remember the exact positive predictive value, but it's fairly lousy, but it's very cheap. We have things like mammography, which there is a big argument about whether it actually saves life, and that's a discussion we can have later. We have colonoscopy, which is not ideal, and many people are not happy about it and are not compliant, and it's expensive, and so in the recent decade there have become more and more tests that do stool tests of various forms to try to essentially get cheaper, less precise, but sufficiently good test for the chance of having a colon cancer. And in the case of colon cancer, because the confirmation is expensive but not that expensive, then you really want this group to be big, and you can allow this group to be relatively big as long as it cuts from the general eligible population quite a lot. And what I want to talk to you today about is a new class of method that made a lot of fuss in the news in the last few years. And so we are going to stop talking about diseases for a second and talk about DNA. We can erase this as well. So as an introduction, when we think of a non-invasive or screening test, the kind of minimally invasive test we talk about is blood tests. All of us have had blood tests, probably much more than once in our lifetime. And the kind of classical blood tests are the ones we talked about in this meeting already, are either counts of cell types, measurements of metabolites or proteins, so individual molecules like glucose, okay, or creatinine, which is a protein, and some more complicated properties like RDW that Amos mentioned, but I'll put those aside. But each one of those readouts, when we talk about biochemical readouts, so we're reading for molecule, has to have its own sensor. So we cannot decide tomorrow we want to measure protein X. We need to develop a sensor for protein X. And protein Y, we need a new sensor, and so on. And so it's actually very expensive to build those biosensors. There are people who are working on building more generic platform for those, but at this stage, this is still kind of a big problem. For molecular biologists, nucleotide sequences, RNA and DNA, are attractive because we have assays that can test for those or read those that are generic. That's why we like our mRNA vaccine, because we can load whatever mRNA we want and it will deliver it, okay? And so reading is very similar. We can read the sequence and then decide what to do with it. We don't care about which sequence it is in order to read it, okay? And so the question is whether this advantage of nucleic acid, can be translated to something that we can test for. And the area that has received a lot of attention in the last few years is something called cell-free DNA. So let's first define the term. Cell-free means it's not inside cells. No, it's not so funny, but and usually when we take a blood test, we can centrifuge it and divide it into, after we centrifuge, we have here a big red mass of all the red blood cells, and then a very small area of white blood cell and somewhat yellowish liquid, which we call plasma. Has nothing to do with the plasma of physicists, but plasma of humans, which is the liquid from the blood with all the things that are essentially soluble in it. Okay? So cell-free DNA is coming from this fraction of the tube, which is about half, depending on the person and so on. And so it's DNA that we find in the plasma. To put a perspective, how many red blood cells we have for ml of blood? Where are the doctors?
4 million?
What?
4 million?
Sounds a bit too low, but
I think you're thinking of cubic millimeter.
yeah.
How many?
For cubic millimeter, that's so we need to multiply by 1,000.
Oh, you said a liter of blood.
Milliliter.
Milliliter.
cc, 1 cc.
There's 10 milliliter by 10 milliliter by 10 milliliters.
Yeah.
About 10 milliliters.
So 4 to the
So 4 times 10
to the 10.
9.
9. Yeah, okay. Yeah.
Yeah, that's not right.
This is red blood cells.
And how many cell-free DNA?
Well, in a second. So,
This is stuff that they don't teach us in medical school.
okay, how many cells that are not red blood cells? I don't know the answer, so if any number I will take, but it's several millions as far as I remember. So, Zach is checking because. And how many? Well, we cannot count cells for self.
About 10 to the 4 cubic millimeters, so it's 10 to the 7.
10 to the 7. So I wasn't that off.
Yeah, pretty good.
Yeah. Okay. So 10 to the 7. When we talk about cell-free DNA, we cannot talk about cells, but we can talk about cell equivalent amount of DNA. So each cell has about 6 picogram of DNA, and a healthy person has somewhere between 5 to 10 nanogram of DNA per ml. That comes out to be, I gave you all the numbers, come on. That comes out to be 10,000 cells. Okay? So the equivalent of 1,000 genomes, roughly, or less, in ml of plasma. Okay?
But it's not the same sequence. So
No, it's randomly selected from a much bigger group of cells. But if you're talking about quantities, just to put things in perspective.
6 orders of magnitude less.
4.
It's red blood.
Oh, yeah. So the red blood, you're saying we were wrong by 3? Okay.
Although,
No, it's for liter.
That's the difference.
Oh, yeah, it's a huge difference.
oh wait, how much of a genome does a red blood cell have?
Yeah, they don't have.
They don't have.
Yeah. Big argument, by the way.
Oh, yeah.
Why? Because of the mechanism? Why is
Yeah.
but why is there an argument? Is there a big argument?
Because when you have production of immature red blood cells, you can have nucleated red blood cells.
Still with that, yeah.
And this,
It's what, less than 1%.
yeah. So the point is that we are looking for something that is very minute amount of material compared to everything else that's in the blood. So we are worried a lot about contamination, and this also puts kind of a limit on what we can look at. So where does this DNA in a healthy person comes from? A lot of research, but basically it comes from cells that die and undergo certain processes of cell death, apoptosis and like, that release the content of the cell to the circulation. And usually we see mostly neutrophils, monocytes. Those who remember Amos's introduction from yesterday, those are 2 types of white blood cells that are involved in non-adaptive immunity, in innate immunity. We see something that comes from megakaryocytes, which is partly from the brain, from the bone marrow. We see some amount of liver, usually few percentage. And again, liver is a regenerating organism that keeps renewing itself at a certain rate, and it's exposed to the circulation. And we see endothelial cells, which are essentially the lining of our circulatory system. And so it's not surprising that when they die, it releases to the circulation. Okay? So that's what we see in a healthy person. Note, I didn't mention T cells, B cells. Well, we see a certain really small amount of natural killer, but not that many. So we see very skewed population of red blood cells and then some other things. So that's a healthy person. And healthy people there's some percentages, but these are neutrophil and megakaryocytes are the bulk, and then the rest are kind of going down slowly. when a person has disease, this picture changes. I'll try to show you, probably I will not get to there, some information about that if we'll get to the presentation part. Oh, we will not get to the presentation part. We have to finish by 4:30. 4. We will not get to the...
4:30.
Okay.
Sorry.
And I promise you a break.
And if you already took this minute to breathe and to think about when we finish, at 4:30 we have a picture downstairs.
Okay, so
please
stay for,
with us.
don't run away, stay for the group picture. Okay, so when a person is sick, for example with cancer, at some point the cancer wants resources and convinces the body to generate blood vessels to provide it with nutrients and oxygen and so on. The cancer is, and again, this I'm super simplifying things we don't really understand, but apparently most of the cancer don't care about quality, they care about quantity, and so those blood vessels are imperfect, and the cancer also keeps invading them. And during the invasion, we get the phenomena that the cancer growth, unlike normal tissue, is exposed to the circulation. And from that, we get two things. We get cell-free DNA, so circulating tumor-derived DNA, which is something called ctDNA. And we also get, and this is a much smaller number, circulating cancer cells, which we would find at the numbers that are single digit in ml of blood for relatively advanced cancer. But they do exist, and the people blame some of those for things like metastasis and so on. And so the question is, can we detect this circulating DNA from those cancer cells that died exposed to the circulation? How would you go about it? Classify what? Okay, use AI. That's a great answer. But what will you do? Okay, you're a very rich person. So we need to ask ourselves, what exactly will tell us that the DNA came from the cancer? Okay, before we go into actually doing this. What's your ideas of what might tell us about how is the DNA from a cancer cell is different from a regular cell? So here a brief introduction to cancer. Cancer is accumulation of some mutation that lead the cells to not stop dividing and to growth, and depending on the type of cancer, sometimes it's very much like what we heard in the morning about bacteria, that there's very channeled set of mutations that you have to go through. For example, pancreatic cancer apparently has to have KRAS mutation, and 2 other mutations are strictly necessary. Other cancers are more permissive and suffices some things go wrong in order for them to actually propagate and to become, to transform into cancer. And another hallmark of cancer is breakdown of the systems that do quality control on cell division. And quality control involves checking for mutations and other problems. So we expect the DNA of cancer cells to be different. And you mentioned mutations, so how are cancer cells?
Can you detect also circulating RNA?
Yes and no, and I will avoid that question. Who asked it? Okay. So how are these different? So one thing is mutations. And depending on who you ask, there is a panel of 70 genes where we should look at mutations, or 300 genes, but there's kind of a who's and who's list of suspects that are often mutated in cancer. So it's not just the whole genome, there are places we kind of associate with cancer mutations that are important. And another thing that's, for the sake of time, I will just spell out the answer is two types of big rearrangement. One is copy number change. So, like suddenly there is a piece of a chromosome that is present for 100 copies because it encodes a gene that really is pro-oncogenic genes. That this is one way of essentially expressing it at very high level. Or it can be a whole chromosome. And essentially something that comes with copy number change is rearrangement, where two pieces of the genome that are not supposed to be near each other become near each other, and in some situation it's a great way to create a monster because you put a very active promoter next to a gene that's not supposed to be expressed, for example, and voila, you have a very high expression of that gene.
Yeah.
Okay.
Is the quantity of DNA also change in order of magnitude?
Okay, so I still want to stay with that, but keep that thought. But if you're talking at late cancer, you're right. There's tons of DNA coming from the cancer for some cancers. Early cancer, this is not the situation. Okay, so increase in cell-free DNA, amount of total cell-free DNA is indicative, but is a very poor as indication. It also can be an indication of a totally different problem, like liver problems. Okay? Yeah?
What about methylation pattern?
Keep that thought. I'm on purpose keeping that for the next, if we get there. So these are changes to the sequence. All of these are changes to the sequence. Yeah?
Do you know which cell produces that DNA?
When I see it, no. Right now, in our story, we don't know. But I do know that because of mutation, if I will find a piece of DNA that encodes for KRAS, is the name of a big who's and who's in this field, and if I find a bit of the KRAS gene and the sequence is wrong in certain ways, I know that it's a cancer-associated mutation. Okay? So the first generation of liquid biopsy methods essentially tested for those panels of genes that are often mutated using what is called targeted sequencing. We won't go into the details, but essentially you can decide you only sequence pieces of the genome that come from a certain region, and that way you can sequence almost all the molecules you can find and see if you find some that have mutations. Okay? Now remember, we have about 1,000 genomes or 2,000 diploid genomes in ml of plasma. So 1 or 2 or 5 of those genomes come from cancer cells. If we want to capture the mutation, we need to sequence a lot of molecules and hopefully catch the one with the mutation. Okay, so looking for mutations, it's targeted, but it's a very narrow, essentially I'm shining the beam of light here and waiting for something to cross it, and I'm not looking at the rest of the room. Okay? But this is the best we knew until recently, and this is very useful in other situations. For example, detecting recurrence of cancer. We know from the primary cancer what to look for, and so we know which mutations are definitely in that person's original primary cancer, so we can suspect that it will be also in the recurrence if it comes. Okay, so there are situations where it's super useful. Yeah?
Without methylations, how do you defer for this?
I cheated. I used methylation for that, but
So what can you tell without methylation?
So-
Nothing, just
so the first-
just mutations and copy numbers.
Yeah, so copy number changes, if there was a big copy numbers, you can do shallow sequencing, so we are not still spending a lot of money. And we're seeing coverage of less than one molecule per position in the genome. But that's enough to see big changes in copy number. Okay? And so you can detect copy number changes, aneuploidities of our sorts by using shallow sequencing. But then usually you do not know anything about the cancer, you just know that there is genomic abnormalities. These were more or less, and you can test for rearrangement using primers that cross the famous rearrangement sites. There's few of those that if they occur, we know what to do, and so they're being tested regularly, but they're not that often apparent. And it's more useful as a treatment decision once we know that there is cancer. So the first generation of liquid biopsies did all of this. And as a screening method, I think we can say today they failed. They're not good enough. Why? So one problem is that we're looking at a very small set of locations. Another problem, and this is something that we get more and more indication in the recent years, but it took a long while to realize, is that yes, there are mutations that we find in most cancers of a certain type, but the logic that if you see that mutation, it came from a cancer cell is actually flawed. There are many cells that have cancer mutations that might be in 10 years they'll become a tumor, or most likely nothing will happen with them. Okay? So the finding of these mutations, we were looking at cancer, so we saw them, but actually if you start looking in a sufficiently good resolution, you see them very often, but not in all the cells in the same place. Moreover, to make life really hard, some of the progenitors of these cells that we see a lot of their DNA in the blood, a clone of a hematopoietic stem cell can acquire such a mutation. Suddenly we see a lot of copies of that mutation in the test, but it has nothing to do with cancer. It has to do with random event and the fact that of clonality in the production of red blood cells. So that's a big issue. And today we use them mostly for during treatment, but not for screening. Okay, so we...
It's also a general cancer. It doesn't tell you what type of cancer. So
well, that depends, depending on the mutation. Sometimes the mutation is very kind of telling you a story, but sometimes it does not. And so we have to think of other things that go wrong with cancer. And so our list continues. So this is like first generation. So several members of the crowd already threw out DNA methylation, so just to bring everybody to speed. DNA methylation is a modification of the DNA molecule that happens in cells mostly when they sort out who they are. Very crudely, it serves as a long-term memory for silencing of particular regions of the genome. And the reason is, and again, I'm skipping a lot of interesting biology, is that because they're on the DNA and because they are sitting at location that are symmetric, this modification is easily propagated through cell cycle. So when a cell divides, it faithfully reconstructs the DNA methylation pattern it had before the division. And so it's a way of keeping information, epigenetic information, because it's not genetic, throughout divisions of cells. And to make life even better, DNA methylation is a very stable modification. It survived. There are people who use ancient DNA and do DNA methylation. So it definitely survived the trip to taking blood and so on, so we can assay for it. So what can we do with DNA methylation? So as I said, DNA methylation is something that is being determined during the lineage, the differentiation of cells. And many findings, including a paper that came in Nature last week from a group here at the university, so we are all very proud, show that there are stereotypical patterns of DNA methylation in different tissues that are very reproducible across people, but very different between different cell types. So there are locations that are methylated only in one cell type and not methylated in all the others. Okay? So these can serve as essentially proxies for cell types. And if we have a good map of those and we can query them, this is where this information came from. So we know about sites that are specific to each one of those cell types, and so we can assay them and estimate what fraction of those sites are either methylated or not methylated, and depending on whether this is specifically methylated or specifically not methylated in the cell type, we can tell something. Yes?
That's all based on population measurement, not specific person.
Yeah. But there are good reasons to believe that these things are reproducible, because what they do is they either silent or not or enable enhancers and promoters that serve to define the cell type. So it's very hard to be an hepatocyte without having the right regulatory program of hepatocyte present, and therefore there is a reason why this is reproducible. Okay? But yeah, so that's something we should remember, that it's not trivial, but those things, there's a pressure to maintain them. In cancer cells, we can find DNA methylation can serve for two roles. One, I mentioned that the DNA methylation is inherited from one cell to its progenies. So if we have a cancer that started as an epithelial cell in the gut and became a cancer, it will still carry methylation patterns that are associated with this type of cells. Okay? And so we can see suddenly something we shouldn't see, which is a lot of epithelial markers in the blood that are not supposed to be there. Okay? And that's a sign that something is wrong, and most likely it's cancer. So essentially we see tissues or cell types that were not supposed to be there show up. Another thing that happens in cancer is dysregulation of the genome, like we mentioned, of those things, also of the epigenome. And so there are promoters that get strongly methylated or demethylated in a relatively consistent way in cancer as another mechanism for playing this game of stopping the brakes and enabling the gas pedal moving forward. Okay? Today there are several companies that sell either something that uses DNA methylation or something that I'll talk to very briefly about in a second, as tools for early detection of cancers. One company that made the news recently is called GRAIL, which stands for the Holy Grail, I guess, of preventive medicine. They have an assay that they claim can detect 50 types of cancers from a blood test. The first set of results from their trial in the UK, I don't know, Chris, if you want to supply information, but essentially they convinced the NHS to partner with them, and they're applying those tests in large amounts in the UK. And they published results recently. The results are promising but not amazing. And of course, they really differ by the cancer types. In some cancer types, they I think, didn't see at all, and others they saw quite a few cases. It has to do with the prevalence of the cancer in the population and with how well their ability to detect methylation patterns from those cancers. And the third thing, which is kind of a bummer, is that different cancers shed different amounts of cell-free DNA due to the rate that cells grow and die in those cancers and other things. So there's also the biology fighting against this. The good thing about GRAIL is because they tested their method on, I think by now, hundreds of thousands of people, they have very good control on what? On false positive rate. Because they've seen a lot of people that most of them, almost all of them, don't have cancer. And so they can tune the false positive rate. The thing that they have much harder time of tuning and convincing us is the true positive rate. So we know about specificity, but we don't know about the sensitivity of those things. And this is before we go into the argument of whether it's useful to detect early pancreatic cancer or other things. Okay. We are going now to do a brief change, and we are going to talk about what exactly happened during cell death. Because I kind of waved my hand and said cell die and release DNA. But it's not so trivial. And the way to think about it, and again, this is total speculation, don't take my word of it, is that when a cell dies, it's like wrecking down a house in order to clear the land. You don't take each brick apart nicely. You come with a big wrecking ball and start breaking up things. So in particular, the way apoptosis works, one of the things that it involves is a bunch of DNases, enzymes that cut DNA, that are activated during apoptosis. Those cut the DNA into pieces, and eventually those pieces are sufficiently small to be soluble, and then they essentially are either packaged into small bodies that are called apoptotic bodies or released to the circulation. The point is that they're not eating all the DNA, they're cutting sufficient amount in order to get the DNA soluble. So in order to understand cell-free DNA, we have to think for a second about what is this substrate that it's cutting. So if you might remember it from those who learn molecular biology, the DNA in our body is packaged into chromosomes. Okay, no? Everybody okay with that? And chromosomes are made out of proteins and DNA. And the smallest unit of this structure that has multiple organization level is something called the nucleosomes. Nucleosome, which essentially is like a disk of 8 proteins. Usually we draw them as 4 and another 4 behind, with DNA wrapped around them once, twice, and 1.8 times. And that's around 150 base pairs of double sequence, of DNA sequence around each one of those complexes. Is the picture clear, or it's my artistic abilities are not amazing? But it's okay. Now, this is just 150 base pair. We have the whole genome, and so what happens is that, and again, I'm doing a very schematic drawing, so if this is the DNA, we have, it's packed on nucleosomes in kind of a regular way, which essentially you try to pack the genome. And what it turns out, not surprising, that the regions between those nucleosomes, so if here is the next nucleosomes, and again, this is totally unrelated to reality, but let's live with it. The area that is tightly wound around the complex actually the DNA is touching a lot of residues of the protein, and is not accessible for the enzyme. While the DNA in those linker regions is very accessible. And so the DNA is cut in a very preferentially between nucleosomes. So we'll get something like that. And sometimes it will eat into the nucleosome, but not much. Okay, so you get pieces of chromatin that are mostly 1, 2 integer quantity of nucleosomes size. Is that useful information? Well, not yet. Okay, so the thing I didn't tell you is that when we have in the genome these nucleosomes, they don't interfere only the DNA, they also interfere with other processes that happen with the DNA. So when we have, I was trying to reconstruct the DNA. So when we have a piece of DNA that other proteins have to bind to, like transcription factors or polymerase, they will be free from nucleosomes. So we'll have regions that are open where other proteins bind. Usually those are things that related to regulation of activity on the genome. These things are not good at protecting from DNases usually, because they're much smaller footprints. But we get those regions that are open. And those regions depend on the regulatory state of the cell. So if a promoter is open, is active, it has to be open. The other way around is not necessarily true. And so a region of an open promoter will be more accessible to DNases and not as represented, will be less representation in the cell-free DNA content. Everybody's...
Can you understand this way the open areas because they were cut? Like the closed areas you catch, and so you can understand the ones you don't catch, right?
Well, that comes into statistics, because to understand, you're correct. When I do take several million cells and do the assay, and they're all the same regulatory program, I see a very clear signal. Here there's nothing, and here there's a lot of sequence and so on. When we take cell-free DNA, which is mixed from all the cells type I erased here and the cancer cell, detecting that you went down is actually, you have to fight with the noise of sampling molecules from the soup. Okay? But but the signal is there. So people started using things like nucleosome depletion, and also essentially cutting sites. Basically, region that is very well packed will have usually a very regular packing of nucleosomes, while a region that is being transcribed, the polymerase works its way around those nucleosomes. So when a heavily transcribed gene, the nucleosomes will not sit nicely in the same positions. They will be in flux. So people suggested, let's look at the location of where we see those cuts and see if they're low entropy or high entropy as an assay for an open region. Okay, since I want to release you in 10 minutes or 15 minutes. I will not use this presentation, but I'll tell you all about that. So all of these things, these two things are called fragmentomics, which is a really cool name. And it's a very subtle signal, because you're looking at the lack of things or the ordering of things. But if you know about 1,000 places along the genome that are specifically open only in a certain type of cell, you can do the aggregation and the statistics and actually extract that signal, even if those are represent only a minority of the cells in your cell-free DNA. Getting down to 5% of the cell-free DNA contribution is something that they can do. Okay? So the several companies that are rivals of Grail use fragmentomics and DNA methylation combined in order to do early diagnosis. Names like Guardant, Phrenomics, Delphi, and several others. Okay, but I want to leave a few minutes for what we do. So we came to this problem as people who study chromatin. We didn't care about cell-free DNA. And why do we study chromatin? Because chromatin, as I said, is tightly involved in the processes that happen in the cell on the DNA. And one type of information that we can look at is indeed the location of those nucleosomes, where we use a very similar assay of finding where are the locations that are protected from cutting by an enzyme in order to map nucleosomes. But a slightly more interesting thing that is known for more than 2 decades now is that the proteins that make up those nucleosomes can be modified. In a similar way that DNA methylation is a modification of DNA, these proteins can be heavily modified. If you remember Ifat's talk, which was yesterday, about modified proteins, this kind of modification, she mentioned a lot of Asians, acetylation, simulation, phosphorylations, and so on. All those things happened on those proteins. Actually, the tail of the histone 3, one of the 4 histones, they're not called 1 to 4, by the way. The tail of histone 3 is unstructured, so it doesn't form structure that we know of. It's very loose, but it's perfectly conserved across from yeast to human, except for one base pair. So it means that there is a very strong selection pressure to keep exactly the same residues, and the modification on those residues are also conserved across all the eukaryotic life. So it's a very important mechanism that seems to be conserved. All of those residues, 40-some amino acids, serve as location for putting information. That's at least the way we tell the story. We didn't, serve as is a big word. And so there are modifications that those modifications are involved in transcription regulation. Part of the process of opening a promoter involves modifying those histones and marking them as a place where transcription will come. It actually serves to bring in some of the factors involved in transcription. Similarly, for processes of silencing, other modifications serve as part of the mechanism of silencing. So it's not just correlates of these processes, it's something that is intimately tied to these processes. Okay? And we, as the big we, the science field, have been studying those modifications for more than 2 decades. We have fairly good understanding which modification appear where in terms of the function. So where is not in terms of cell type or type of gene, but rather type of process. So the same modification will happen on activated genes in all cells, but those will be different genes in different cells. Okay? Why is this useful for cell-free DNA? It turns out that more than 20 years ago, people have shown, actually some of the earliest cell-free DNA work in the field showed that cell-free DNA is not cell-free DNA, it's actually cell-free chromatin. It's pieces of chromatin that the DNA is upon. So most of the DNA that we find in circulation is actually bound to histone proteins because this is a very strong electrostatic interaction that it takes a lot of energy to open, and the wrecking ball doesn't care about it when we talked about cell death. Okay? And so the question we ask is whether those modifications that we have in the cell survive the trip through cell death, circulation, getting collected in the test tube, in the blood collection tube, the plasma separation, the freezing, and so on. All the torture that we make the plasma go to. But assuming for a second that it does, essentially, if we think of it from information perspective, those here it is. We usually in our presentation draw those as flags because it's easier to talk about. So suppose the green flag is a marker of active gene. Green for go. Okay? If this information is preserved in the circulation, it means that when we encounter this molecule, we know two things. First, we know the DNA sequence if we will care to sequence it. But if we know about the modification status, we can say this DNA sequence served as an active gene in the cell it came from. Okay? And so that information is by itself super interesting because genes are expressed in cell type dependent manner, but also in terms of cell state dependent manner. Inflamed cells look different than regular cells. Activated macrophages is different than resting macrophage. So many changes in the cell state are reflected through the regulatory program. Okay? And so the basic idea of the assay is that we're using capture and sequence. So we capture things that have green flags from the circulation. So we enrich for molecules that come from open promoters. And then we sequence what we caught. Map it back to the genome and get a map of all the active genes. Easy peasy. So because of the small amount here, it's actually a fairly challenging task. The green mark is really nice because it's a mark of active promoters, so it's very specific to specific location. Active promoter means the beginning of a gene, which means that less than 1% of the nucleosomes in a cell have this mark. So we were talking about 10 to the third cells, but the amount of DNA we capture is actually much smaller. So this raises a whole bunch of technical issues that luckily I'm working with talented people who solve them and actually in a very impressive way. And we have an assay that, from our perspective, give me for each gene how many molecules we saw in the assay coming from that gene. And one of the nice things about it is that all the locations that don't have the mark do not show up. So this question of how much I'm going to spend on sequencing things that I don't want to see disappeared because the biology pre-selected those things that I'm interested in. So we can look at the whole genome and not decide about targeting specific genes or specific locations and so on. Okay, now comes a minor problem, and I'll leave you with that problem. And so as I said, we get a map. So, and after some amount of processing, essentially it's a vector from gene 1 to gene, 25,000. For genes in the genome, how many molecules we saw for each gene. And these molecules came from this population of cells that contributed to the cell-free DNA pool. Remember, neutrophils, monocytes, megakaryocytes, liver, endothel, and maybe cancer cells. And maybe, if there are other diseases, it turns out that the other tissues also show up. Okay? Now, when I look at this, I don't know which one came from where. So luckily for us, if you look at the low-hanging fruit, there's some genes that we can mark. I'll mark them by red. That we don't expect to see ever in all the tissues that contribute to the healthy cell-free DNA pool, and we do expect to see from cells that come from a tumor. Let's say colorectal tumor. Okay? So these are essentially sensors that if they light up, I smell a problem. Okay? And it turns out this is good enough for many interesting applications, even if there's the background of everything else going on. And Gabriel had a poster, I think it's not hanging down there, but we can return it tomorrow, that shows how we can use it to find subtypes of a cancer based on the gene expressed in the tumor, because different groups of genes are marked in the different subtypes and we can detect them. So it's actually, we can get a long way doing that. The problem is that some of the most interesting applications, for example, talking about a subpopulation of T cells that we don't expect to see in healthy people, but we see in some type of reaction to, for example, autoimmunity or to immune checkpoint blockade or things like that, are very similar to many other cells in the immune system. And so to really differentiate between them, we have to start talking about the numbers that we see for different programs and their relationship. And essentially the way to think about it is that this vector is actually, again, using linear algebra, is a matrix times a vector of proportion, and this vector is cell types or states versus genes. Okay, so think essentially somebody takes these columns and mixes them up in some unknown proportion in order to give the final output. Now that sounds easy, If I know this matrix, I can invert in linear algebra. And again, this is where life comes to bite you in multiple ways. First of all, we don't have this matrix. And our approximation for this matrix proved to be much worse than we expected. Second of all, things that have low probability, the sampling noise is actually starting to be important. So you have to take into account that we're doing discrete Poisson sampling from populations of cells. And finally, because we're sensitive to the state of the cells, there are many changes that the same cell type can undergo, which are interesting to see, but will show up as essentially variation on those columns in the matrix. And so this is starting to be a slightly more interesting problem. And because you were saved from my presentation, you didn't see, but we have by now thousands of samples from healthy people and several hundred samples from a whole range of diseases. So we moved from the very data poor situation when we developed the method, where we had 10 samples and we were like, wow, to a situation where we're starting to be in the data rich world, where we say, maybe just let the data teach us what is this matrix and forget all the experiment other people did with methods that turns out to be unclear, that give us guesses about what this matrix should be. Just let's reconstruct blindly. But the real thing we want to do is actually kind of combine those two things. So this is where I put the AI in my research. I promised Michal And since I didn't have slides, we don't have the thank you slides, but this is collaboration with a lot of people and my group. Yuval, who is a researcher in the medical sciences, who essentially was one of the pioneers of DNA methylation, and from our perspective did the heavy work of convincing people to give IRB for this kind of assays and to make the connection with the doctors for collecting samples. So we came in and had easy time getting our hands on samples. He's also very smart and suggested a lot of important things. And many doctors and researchers for computer science, including Morse hiding there, and Tommy Kaplan and a few others. And so it's a very large team effort to get this working, but this is something that is actually interesting, changed my life. My group stopped working on chromatin in yeast or on COVID, but instead doing just this. And all we do is decompose matrices these days. And Gabriel can tell you more if you're interested. He's been with us since the beginning and knows all the analysis side of this in and out. There was a publication last year in Nature Biotechnology, so if you want to read about the method and see some nice pictures, it's there. And thank you very much. Questions? You've kind of exhausted during, so you don't have to.
Why AI came so late in the talk? Why don't you use AI at all? And you didn't have the data yet?
We didn't have the data yet, yeah.
But do you foresee that AI would be the tool for you to...
Yeah, because we're right now at the stage where everything else is streamlined. And now you can start, we're collecting 100 samples a week roughly, and it's going to be faster. And so you start seeing a lot of data, and that allows you, and again, slides I didn't show, there are all kind of cases where we follow the same person over several weeks, taking one sample every day, and we see changes and they correlate with things that we know happen to that person. And so we have a lot of prior information about those samples that can help us tease out things. But, so this...
Another question, related question. So predictions and all kinds of interpretations and clustering, that's obvious.
Yeah.
Do you expect any causal analysis in your study?
There is a causal in the sense that that we're going to look at samples of patients before treatment and then try to see what happened to them and try to see if we can see signal that...
By design or with
No, so this is not by design. This is essentially association, and the fact that this was collected before the treatment suggests that it's at least upstream or more likely showing us something about the state of the patient that relates also to the response to the disease. But that's a very weak notion of causality, but not what we're looking for.
We don't have to. If it doesn't serve, it doesn't serve.
Yeah.
No, I mean, maybe on that point, it's interesting, but like in screening programs, like in the sense that causality doesn't matter because, as you said, it could be downstream, and often we'll get a biomarker that's a downstream of a causal, the actual disease itself, and that doesn't matter.
Yeah.
Because, as you quite rightly point out, you'll then go for a more invasive test. So actually, as long as it's predicted, it doesn't matter if it's reverse causation, it's happening after. Like you could have you could be asymptomatic, and what you're trying to do is pick up a molecular symptom.
Yeah. And the symptom, by the way, doesn't have to be the tumor cells. It could be the immune cells that respond to something going wrong. And it won't have any specific mutation, but the signature of immune activity in the colon might be sufficient to say something is wrong there.
You surely, if you want to show that your technology works, you would have to apply some causality to show that the prognosis of those people who used your testing was better, and it's probably not going to be...
No, at the end of the day, you do a trial. You collect a blinded trial. 1,000 people went into colonoscopy, and because they did colonoscopy, we know what was found, and whether we predicted that we got them blindly and how well did we do in predicting that. That's a very standard trial. And that's what the FDA will ask for.
But now that you raised it, I realized that I already told someone that you didn't want to talk about it. But it seems to me that since you talked about the immune cells, doing a single cell seq profiling of blood might in fact be a high performance way to look at the immune system and say, are you seeing any tumor cells?
Okay, so just to translate what Zach said, the immune system sees a lot of things.
Did I deserve that?
No.
I deserved it. I actually deserved it.
The immune system sees a lot of things, and we can sample the immune system by taking a blood sample. This is 10 to the 7 million cells, and if we look at them, we might be able to say what they've seen. And indeed, this is a lot of useful information there. The thing is that most interesting action doesn't occur in the circulation, but rather in tissue. And so the T cell that decides to expand and attack, it's doing it not in the circulation, it's doing it in the tissue. And the cells you'll collect in the circulation might tell you that the certain T cell receptor has shown up, but it actually will be really hard to find it among all the others, while a local explosion of proliferation and cell death because something is happening is actually showing up in the circulation. So this is a very nice story. I can't prove it yet, but it shows what are the differences. At the end of the day, we'll use whatever methods that work, but this is why the potential for seeing this.
So what fraction of the cell-free DNA needs to be cancer for you to detect?
In theory or in practice?
So in practice.
In practice, it's really hard to prove. I mean, we can do, titrations and show things. In theory, the bigger the territory that is specific to the cancer, the more sensitive it becomes. The three factors that essentially are crucial is how many molecules are unique to the cancer compared to the background, and then how good I am in terms of capturing molecules and how specific, because there's always also non-specific capture molecules. One of the things that we did in the company that we formed for early detection is really improve the sensitivity and specificity of the assay in terms of capturing molecules. We moved from about 1 to 100 signal to noise, which, remember, this is 1% of the genome, so it's 50-50, to about 1 to several thousand, so we actually barely see background. So that increases our ability to detect things. The real question is, we don't have good, late cancer is not a good proxy for how early cancer looks like. That's I think, is why I'm hesitating to give you a number. And within a year, I could give you an empirical number based on a real test, and that would be, but that would be include also the variation in the percent present in the blood of the patient. So it's not exactly what you asked. But I will have much better estimate because I will know what early cancers look like.
So you're doing this on colonoscopy?
So the commercial, so just to be clear, the proper disclosure, I'm founder of a company called Sensira that does this for early detection. My group does a lot of research for other applications. And Sensira is doing a trial with colonoscopy, serial colonoscopy. Everybody comes in, is trying to get recruited, and then we compare what we got to what the pathologists report. And that's the way you prove things work. And then you discover that life is much more interesting. As Amos said, classifying colon cancer or healthy is actually doesn't cover what you actually find in the wild, because there are many other things that people have, and we see them. And it's interesting, but it might not be relevant. Yeah. I think I bored you enough. We're going for a group picture, and then Zach is going to pay for all the questions you ask now.
Absolutely. What?
So thank you.